Hello students, welcome once again to our course Metallocene and Metal-carbene based organometallic compounds for industrially important advanced polyolefin catalysts. So far what we have discussed how the CP ligands, that is the cyclopentadienyl ligands, can interact with metal d orbitals, how the pi orbitals of the CP ligands undergoes the linear combinations and forms a set of ligand group orbitals, and then we have taken the approach of forming the molecular orbitals through symmetry adapted linear combination of molecular orbitals to construct the molecular orbitals. And why we constructed? Because to understand the orbitals and understand the nature of the HOMO, and to understand the electronic properties of the orbitals in the metallocene. This is very important to understand the reactivity and the structural parameters associated with metallocene. So far we have discussed the parallel metallocene, where CP ligands, two CP ligands are parallel, like ferrocene, that is the classical example. Although CP ligands can exist in two forms, one is the eclipsed and one is the staggered. So that we discussed. The molecular orbitals are similar for the eclipsed and staggered. Eclipsed symmetry group is D5H, staggered is D5D, only the symmetry level of the resulted molecular orbitals will be slightly different. That we discussed in the last class. Now, I have very briefly shown that the catalysts, metallocene based catalyst for olefin polymerization, which we will be discussing, and that is our main interest in the course, are falls in the bent metallocene. So it is not like a ferrocene, okay, but it is like a bent. Now we have to understand that what does it happen if the CP rings are tilted, like bent. What will be the difference in molecular orbitals? This is very crucial to understand, because without this understanding we will not be able to understand the reactivity and the mechanism of these catalysts. So let us discuss the bonding and electronic nature in bent metallocene in today's class. Okay. So just in a brief points, which concepts will be covered. We will cover what are the bent metallocene, how the bent can be created, okay, in the metallocene, then bonding in the bent metallocene using molecular orbital theory, and then definitely the purpose is to understand the electronic structure. So these are the key points: the electronic nature, structural variation, and bonding in metallocene, which will be discussed in today's class. Okay. So in the last classes, okay, if we remember that we have understood very systematically that what are the pi orbitals of the CP ligands, that is this one, that is the sigma symmetry, that is the pi symmetry, and that is the delta symmetry. What we did? We then checked the symmetry of these pi orbitals, and that is the LG orbitals of the two CP ligands, okay, the two CP ligands, and then we tried to match with the atomic orbitals of the metal, and then we constructed molecular orbital theory, and this process is called the SALC. SALC means symmetry adapted linear combination. So what we did here, basically we did the combination of the molecular orbitals of two CPs plus the atomic orbitals of metal. Okay, for let us say for 3D transition metals, which atomic orbitals we took? 3D, 4s and 4p. So, that we discussed. Okay. And just to refresh, here you see that this one, okay, as I told that the molecular orbitals will be very similar for the eclipsed and staggered conformation of the ferrocene, but only the labeling will be slightly different. Okay. So, here you will see that this is the A1G, okay, that is the this one. So, this is the LGO after addition, okay, of this 2 CpA1. So, now this is perfectly matching with the dz square. So, this is perfectly matching with the dz square, you see, okay, and also it will be fine for S, and then we formed we then checked and did the SALC method to construct the molecular orbitals. Similarly, for E1 you see that also we checked the specific symmetry of the d orbitals, and then we constructed the molecular orbitals of the iron Cp of parallel metallocene, as example iron Cp2 molecular orbitals. Few things we noted, this is very important because we have to understand the difference between the parallel and the bent metallocenes. Okay. So, in the last class we discussed that Cp minus is a poor sigma donor. Cp minus is poor sigma donor, because if you see the molecular orbitals, okay, if you remember, so this you see this is the Cp minus is highly stable. Okay. So, it is very slightly contribute in the bonding, and similar way the Cp minus is also a poor pi acceptor due to the energy mismatch. Okay. So, not good pi acceptor and also not good sigma donor, and also we discussed that these are the main interest E2, A1 and E1. This is actually the antibonding, slightly antibonding nature, although we discussed in the last class that E1 although it is antibonding, but the antibonding character is not really pure, okay, is slightly antibonding in nature. And similarly, for E2 and A1, okay, these are the bonding character is not pure. That means, it is E2G and A1G are slightly bonding and slightly bonding, okay, and this one is not significantly sorry. So, this is not significantly antibonding. So, okay, fine. So, for the metallocene compounds, okay, you have to be, we are actually interested of the orbitals you see. So, this region, I am okay, this region. Okay. So, the filling up of these 3 set of orbitals, that is the E2, A1 and E1 star, actually will dictate the properties and the stability of the metallocene compounds. Okay. So, we will try to understand the difference between the parallel to the bent metallocene. So, the molecular orbitals for the parallel metallocene is important, otherwise we will not be able to understand for the bent metallocene. So, also you have to be you have to understand that this is, we are considering the D5H symmetry, okay, and you have to understand that what will happen if it is bent, which symmetry, because the symmetry will basically dictate the orbital's energy and the symmetry, which will be important to construct the molecular orbital or molecular orbitals. We will see in the next slide. So, you see that, and also in the last class we discussed that the major contribution for the stability is actually the E1 G, okay, or E1, okay, plus the 3D. So, these are the major interaction for the stability of the metallocene, parallel metallocene compounds. Okay. Fine. Now, we will see that what are the bent metallocene compounds and what will be difference in from the parallel metallocene compounds. So, here you will see that this is the ferrocene, this is the staggered. So, that is the D5D, okay, and if it is eclipsed, then it will be of course the D5H. This is the bent metallocene, you will see, okay, bent, and the L may be, number of L may be 1, 2 or 3. So, this L here I have shown with 3 L, but here there may be 3 L, there may be 2 L, there may be 1 L, depending on the metal centers and oxidation state. And this is the half sandwich complex, that is also lovingly called the piano stool complexes. So, here only one CP rings, okay, and one CP rings, and here the more than one CP ring in other cases, here more than one CP rings, and in this case half sandwich complexes, the other ligands will be monodentate. These were monodentate, okay, or bidentate or tridentate, okay, but not CP ligands. So, these are the categories mainly are found in metallocene chemistry. Okay. Fine. As I told that we will be interested for this category of the bent metallocene and this category of the bent metallocene, because later you will see that most of the metallocene based catalysts have the structure either the C category or the D category. So, it is important to understand first that what is the electronic nature and the orbitals of this category, that is the bent metallocene, where you have a 2 CP rings which are not in parallel bent, and the other also have ligands, that ligands may be alkyl or aryl, halides, or number will vary from 1 to 3. Okay. Let us try to understand the electronic nature of these bent metallocene. Fine. Okay. So, before going to the molecular orbitals and to understand that what orbitals are involved in the interaction, so I will just first try to give some highlight that how the additional parameters can be imposed in metallocene for its variation in structure. These are important because you will see here that what we have done, that these are the CP ligands, where these are free CP ligands, 2 CP ligands are not connected. Now, if these 2 CP ligands are not connected, then what will happen? Because this one will rotate, okay, because these are free. So, this will rotate, as example it happens for ferrocene. Okay. You will get the eclipsed and staggered, and the barrier energy is very small. okay, 4 to 5 kilojoule per mole. So, similarly, this will also rotate like this because these are free. Now, if I do something, okay, if we how we can restrict, okay, you have to, if we can bind together, okay, thread it, okay, these two CP ligands, then the movement or the rotation will be restricted. So, here if it is like this, so what we have done, these two CP ligands, okay, this is actually called indenial ligands, fused CP ligands. These ligands have been threaded by some linkers. Okay, here this is basically the ethane linker. Okay. So, what we have done here now it cannot rotate. So, rotation is restricted. Rotation is restricted. Okay. So, now your symmetry will be different. Okay. Now, here you will see this, what are the symmetry here. Okay. So, this is, you have this is, if you consider this is C2, okay, this line is C2. Now, this plane is this sigma V. So, symmetry will be C2V. Okay. Now, here the symmetry will be now different, and also there will be no restriction. And also there is restriction in the movement. So, there, if we make a chiral ligands, okay, with this threaded, then the chirality will be permanent. Okay. So, there will be no possibility of getting the racemic mixture by the rotation of the CP ligands. So, this kind of bent metallocene is called ANSA metallocene. ANSA is that you see that this ring is closed in different atom. If this is closed, so I am just telling, like, if you have like this scenario, okay, suppose you are, if you are forming a ring here, so this is called ANSA. Okay. So, ring closing in to other atom of different CP, and if you close the ring like here, this will be spiro. Okay. So, you understand what is the difference between spiro and ANSA. Okay. Fine. So, this will be our interest in the following classes, and here you will see this is basically the example of half sandwich metallocene complex, because here will be one CP ligands here you see. Okay. And these are, as I told, that there may be chelating ligands. Okay. So, here may be monodentate, may be chelating, okay, to satisfy the coordination of the metal center. So, this kind of complexes is called the half sandwich metallocene complex or the constant geometry, because this is in high constant, okay, this ring. Okay. So, as I told that in this category this is also bent, but here the two CP are not connected here, and you will see that this here it can vary, there may be one ligand, two ligand and three ligands, but now we will try to understand in the bimolecular orbital theory that how these bend happen, and that bending will influence which parameters, okay, and how it will dictate its reactivity. Okay. So, not only the simple CP, you will see that different type of CP ligands are reported and possible in this metallocene chemistry. Here you will see that this is the examples of chiral and non-racemic CP ligands. So, here is a planar, you will see. So, this is a planar. So, these are you will see that but this is this CP is planar, but here you will see there is a chiral center. So, what happened? This moiety has been installed in the planar indenyl group. So, now this ligand is become chiral. So, as a whole this ligand is become the chiral. Okay. So, this also the chiral, this also chiral. So, you will see you can make. So, this is I am showing the design, I am not showing the real catalyst, I am just showing the design or strategy, okay, to make the chiral CP complexes. Okay. So, you can here I am just showing the simple CP ligands. Okay. It is maybe CP, just maybe fused CP like indenyl. We will also see that other kind of CP fused CP ligands like fluoronyls also possible, and in this case you will see these CP ligands are further functionalized to make the chiral ligands. So, here you will see all are the chiral and non-racemic CP ligands, which will be important, okay, in future classes to understand that how we can make this metallocenes chiral and to get a specific tacticity of the from the prochiral monomers. Okay. So, here you will see that you can make the unsymmetrical. So, if these are, you will see that here we are putting the chiral moiety here. So, here we are what putting, we are installing the chiral moiety to planar CP, and here what I am doing, we are trying to make, okay, converting planar CP, okay, converting planar CP to induced chirality. Okay. So, how is possible? If you put the two unsymmetric R groups, okay, then you are now you have now destroying the plane of symmetry, and that is why you are now inducing the chirality. You can make here two possibles, in a two enantiomer possible. Let us say if I name is S, it will be R. So, one very simple CP based ligand is this one, okay, the unsymmetrically substituted phenyl and methyl. So, from there you can make two enantiomeric metallocene compounds. Okay. So, unsymmetrically substituted CP complexes, you will give enantiomers of the metallocene. So, these are very important in our future classes, how we can make the chiral catalyst and how the enantiomeric pure catalyst will give a different tacticity when compared to the racemic mixture of the catalyst. That we will discuss in the future classes. Okay. Fine. Now, so let us come to the our main discussion today's, that is the what are the unique structural feature from a parallel metallocene to a bent metallocene. Okay. So, I am going slowly because it is very important to understand this feature. So, this is, you see, this is the parallel and this is the bent. So, as I told that L may be here in this N may be, okay, 1, 2, 3. Okay. So, some examples of the bent metallocene is this category. Here zirconium is in 4 oxidation state, tantalum is in 5 oxidation state, okay, and this is the D0, this is 16 electron system. Okay. So, this is also D0. Okay. We will understand this one very systematically. Let us, okay, fine. So, here you will see that this here, that if you draw a centroid, so this angle is, okay, how much angle will be? Centroid, metal and centroid is almost 180 degree. Okay. But this one, if we centroid, okay, So, this is not 180 degree. So, there is some structural parameters associated with bent metallocene which will be interesting and we use to quantify how much it is bent. Okay. So, one is the main angle of interest is this beta. Okay. So, beta is basically this is the centroid. Okay. This is the centroid and this is the centroid, and you this is the plane of this is the CP plane and this is the CP plane, and you extend, and the angle, this angle is called the beta angle. So, this is a important structural parameters to quantify that how much bent it is. This one is the centroid. Okay. This is, you just assume that this is the centroid. So, centroid of the CP ligands, metal and centroid, this is the alpha. This also clearly quantifies the how much bent it is. Okay. And this one also, okay, one important structural parameters, that is the bridging atom. Okay. So, it is easier if it is there is a single atom. Okay. Sometimes the bridging is consisting of the multiple atoms. So, here centroid, the bridging atom and the centroid, that is also important structural parameters. Now, from here you will see, okay, that if beta is so it is like a crocodile mouth. Okay. So, if you see beta is small, it will be like this. If beta is big, it will be like this. So, what is the consequence? If beta is small, then there is more openingness. Okay. So, if beta is more, okay, means the more opening in metallocene wedge. Okay. So, and what is the consequence? The consequence is that it will be that substrate can approach very easily here. So, if beta is small, then there is less opening. Okay. So, it is like you can assume like a crocodile mouth. Okay. So, if small, okay, and if it is big, so is a more space here, okay, for the substrate to approach. Okay. So, there will be less steric hindrance in this side, Okay. So, less steric, that is more openingness, okay, for more beta. Okay. So, that we will try to understand in the by using the molecular orbitals, and we will try to constitute from the parallel metallocene, so that we can understand very easily. Okay. We will just try to compare what will happen if it is bent metallocene, okay, from the parallel metallocene. Okay. So, in the next class, okay, we will try to understand that if we decrease the symmetry of the metallocene, okay, then what will be the impact in the metallocene compounds. As I told that this is the D5H, this is the C2V. So, what we are doing? We are basically decreasing the symmetry, lowering the symmetry. So, what will happen if we do it, okay, and what will the impact in the molecular orbitals diagram. So, in the next class we will continue these molecular orbitals and the understanding the electronic nature for the bent metallocene, which will be very important to understand the reactivities and the properties of the bent metallocene, because our metallocene based catalyst for olefin polymerization actually falls in the under the bent metallocene categories. So, thank you very much. We will see in the next class again.